Hello, everyone. So we are following up with our webinar, Practical Utilization of New ACI Code 440.11 on GFRP Reinforced Concrete, which took place on last Tuesday. So we received many questions and we decided to go with this additional section, and we really thank our speaker Will, who graciously accepted that he will answer few questions, or many questions, I guess. So we will this session is for answering the questions. So we will start with our first question to Will. So there was a question regarding the service loads. So for GFRP reinforced concrete, is there any work going on, or how the long duration service load are handled?
Sure, great question. And first of all, just like to say it's great to see so many questions that came in on the presentation we gave last week. Glad we could spend some time to answer as many of these as we can, since we didn't have much time during the webinar. But related to that question regarding exposure to long-term sustained loads, that is something that I wasn't able to cover during the talk, but that is one of the design issues that we do face with GFRP reinforcement. GFRP materials and FRP materials in general do have a limitation in terms of how much sustained load they can carry. This is a property of FRP materials called creep rupture that comes into the picture. Creep rupture is if the material is sustaining load, it creeps over time, and if that creep finally exceeds its elongation capacity, it can suddenly rupture due to that sustained load. So creep rupture is a known phenomenon with FRP materials, and we do build in design criteria to avoid that. So the 440.11 document, speaking specifically about GFRP, puts a limitation on the sustained service stress that the material can undergo. And that limitation on sustained service stress is 30% of its ultimate strength. So it's essentially a service load stress limit on the FRP bar itself. Again, one of the design checks we have to do when designing GFRP reinforcement, and also can be a limiting factor. Again, oftentimes these things like serviceability criteria in general can be a limiting factor for the design, and the creep rupture stress limit can certainly be a limiting factor in design. Making sure that we're using enough reinforcement to avoid that creep rupture failure can be a controlling factor in the design. So great question, and certainly something that we have to think about when designing these things.
Okay, great. Thank you. So our next question is regarding the cost, because you talked about the cost, that GFRP will be more cost effective as compared to the steel. But does the cost include design cost? And also, like you said that this material will also have some labor saving, but in many cases, this is not passed to the owner. So do you have any comments regarding that?
Sure. Yeah. So I'm by no means an expert on where costs are currently with GFRP. I know that GFRP, generally speaking, is cost competitive with things like stainless steel, galvanized steel, epoxy coated steel, and in some cases can even be cheaper than regular mild reinforcement if the particulars of the project are fall in a certain range, I would say. But the design cost, though, again, I don't do this professionally for a living anymore, so I can't tell you what the design costs actually are, but the design is much more involved. You know, we've talked about that during the presentation, that there's a lot more factors to consider with designing GFRP. So conceivably, design costs can certainly be higher particularly with an engineering firm that doesn't have familiarity with it, that has to get over the learning curve, that type of thing. So certainly design costs can factor into that as well. But I think the important thing to note is just that the cost of the actual material itself, I think there's a perception that FRP is a very costly material, and the reality is that it is getting to be much more cost competitive with traditional steel reinforcement. Then relative to the question about whether labor savings are passed on, so that is one of the big cost components with FRP, that there is a savings in terms of labor and increase in productivity using FRP bar. I would say that right now, I don't know how, if the industry is mature enough that contractors are aware of that and that they're building that into their bid pricing. I know that in a lot of cases, contractors bid at the same price as they would bid steel, and then if they do realize any cost savings, that's just additional profit on the job. But I think that, as the industry matures, you might start to see those labor savings actually being factored into bid pricing, and those costs being realized, those cost savings being realized by the owner. But I think right now that may or may not be the case, just depending on how the project is bid and what the particulars are of the project itself.
Yeah, and on the same lines, I would like to ask, many manufacturers, they do sell the GFRP, claiming that it is one-to-one replacement for steel. So what do you say about it?
Sure. So I've heard anecdotally similar things, that some manufacturers might tout FRP bar as being a one-to-one replacement for steel. And throughout the presentation, I tried to highlight there are a lot of differences with GFRP versus steel. There's differences in modulus. There's differences in how we calculate certain things like shear capacity of members and that sort of thing. So it's certainly not the philosophy of the 440.11 code that there is a one-to-one replacement steel to GFRP. Typically speaking, you are going to be using more GFRP than you would steel. So you're either going to be using larger bar diameters, or you're going to be using more bars, GFRP versus steel. There might be a few cases where that's not necessarily true, and there might be some conditions where maybe there would be less GFRP reinforcement, but I would say that it's not the case that it's just simply a one-to-one replacement. You have to go through the exercise of figuring out exactly how much GFRP you need, and it is going to be a different answer than figuring out how much steel you need.
Yeah, I think to go in detail, we have few questions on designing, which I will be asking. So the first question is the minimum area for GFRP for a given section is similar to the steel rebar?
Yeah, and again, I think getting back to the answer to the previous question, the answer is no. Generally speaking, there's going to be a larger area of FRP versus steel, just depending on the particulars of the design.
Okay, so, and the other question is, what is the difference in the shear capacity of these GFRP versus steel rebar? So I don't know if you have an approximate answer for it, or it's
yeah, so I guess not quite clear whether that question is getting at the actual shear strength of the bar itself or the shear strength of a concrete member reinforced with FRP. So I guess I'll answer both questions. The shear strength of the bar itself is roughly about half the shear strength of a steel bar. The ASTM D7957 spec for GFRP bars does specify a minimum shear strength. The minimum specified strength is 19 KSI in shear. You compare that to a grade 60 steel rebar, which has a shear capacity of somewhere around, I think, 36 KSI. So the GFRP bar, again, is roughly about half the strength of that steel rebar. But again, that can vary depending on the exact manufacturer of the GFRP bar. But just based on ASTM minimums, that's about where it would fall. So again, it does have lower shear capacity than steel does. Then relative to if we're talking about shear strength of concrete members reinforced with FRP stirrups, the FRP stirrups are, there are stress and strain limitations that we put on the stirrups when we use them for shear. There's reduced capacity of the stirrup because of the bend that the stirrup makes. There's a reduction in the capacity at that bend location. And then getting back to the shear capacity of the bar, there is lower shear capacity of the reinforced concrete because longitudinal FRP bars don't provide as much shear and dowel action as steel bars do. So all of those things factored in, again, you generally end up using more GFRP shear reinforcement than you do steel reinforcement to get equivalent shear capacity.
So I get it that this GFRP reinforcement is different than how the steel reinforcement. So if we talk about the slabs, we can see that the cover noted is not different. It's mostly same for GFRP reinforced concrete and steel reinforced concrete. So can you clarify like why how this adjustment could be done or like for this material?
So the cover requirements are generally about the same. Part of that is because of the difference in the transverse coefficient of thermal expansion of the bar. I think I mentioned this during the talk, that FRP bars have a higher coefficient of thermal expansion in the transverse direction than they do in the longitudinal direction, and they also have a higher coefficient of thermal expansion than concrete does. So essentially, as you undergo thermal cycles, the bar can potentially grow at a faster rate than the surrounding concrete. So you have to have enough cover around the bar to prevent splitting, cracking from occurring. So the cover requirements from that standpoint tend to be the same. Plus there are other factors with cover, like cover requirements for casting concrete against the ground. That's more of a constructability issue with reinforced concrete. It has nothing to do with the material the bar is made out of. So a lot of the cover requirements that are in ACI 318 would still apply to FRP reinforced concrete, just because they're more constructability issues.
Yeah, so like there are a few questions regarding how can we use hybrid reinforcement, or can we use GFRP rebar combined with steel rebar, or can we use metallic ties with GFRP bars? Are those allowed or not? So there are like maybe 4 or 5 questions regarding hybrid reinforcement. So do you want to talk about it?
Sure. So it's a great question. So the answer is yes, you can use the two together. However, 440.11 does not cover that. So there aren't provisions in 440.11 right now for, say, doing longitudinal steel reinforcement and shear reinforcement out of FRP. We don't have code requirements for that right now. But that is something that could be done. It would have to be looked at. There are certainly several examples out there, particularly where you're looking at maybe FRP as a top mat of reinforcement and steel as a bottom mat of reinforcement in, say, a bridge deck or a parking deck. Again, relying on the FRP at the top for corrosion resistance and the steel being at the bottom is going to, chlorides and carbonation isn't going to reach the bar as soon. So those types of things certainly have been done, but again, the code doesn't specifically cover that. Then relative to metallic ties, so FRP bar can be tied just like steel bar. You can tie it with metallic ties. That's not a problem. There's nothing like there's no like galvanic reaction between dissimilar metals or anything like that. GFRP specifically is does not have any type of galvanic reaction with steel. So you can use metallic ties with FRP. In some applications, though, you're trying to get away from any metallic material in the concrete. So maybe it's for an application where you're looking at the non-magnetic properties of FRP. In those cases, you would want to use plastic just to remove the metallic material from the equation. The one caveat I would mention is that if we're talking about GFRP bars, there isn't an issue. If we're talking about carbon CFRP bars, then there is potentially issues with galvanic corrosion. So tying carbon bars with metallic ties probably would not be a good idea. But that's, again, specific if you're dealing with carbon bars.
Mm-hmm. Thank you, Will. So as we were talking about how 440.11 is very similar to ACI 318 layout, there is a question regarding it. Like the previous 440.1 report noted the use of subgrade drag for slabs on ground. Since the new manual mimics ACI 318, it would point us to ACI 360. So clarify if that means ACI 360 would therefore control, or ACI 440.20 would. I don't believe those documents allow for GFRP at this time. Is that correct? I read this question, so.
Yeah, so it's a great question. The language in the 440.11 document is very similar to 318. So it says, I think, pretty much exactly what 318 says, which is that it does not cover the design of slabs on ground unless the slab is transferring load. I can't remember the exact verbiage, but 440.11 does mimic that language that's in 318. And similar to 318 in the commentary, it does point the reader toward ACI 360, which is a guide for design of slabs on ground. So that language is in 440.11. It is also true that the 440.1 document, and sorry, I know the numbers get a little bit confusing, but the 440.1 document is the original guideline document for the design of GFRP reinforced concrete that's existed for almost 20 years now, over 20 years now. That document does have some good guidance for the design of slabs on ground. And you can absolutely still use that document. It is still a valid document. ACI still publishes it. You can absolutely still use that section of that document to design slabs on ground. And in the commentary to 440.11, it does direct the reader, if you're looking for designing slabs on ground, you should look to ACI 360 combined with ACI 440.1. Again, both of those documents are guidelines. Neither one of those documents is a code. So they are referenced in the commentary. They are not code language. But if you're interested in using FRP for slabs on ground, you can certainly use 360 in conjunction with 440.1.
Yeah, I think this makes clear about the documents. Yeah. So our next question is, would it be appropriate approach for cast in place and post installed anchorage to treat it as anchoring in unreinforced plain concrete?
So that's a very interesting question. So I imagine the question is getting at if you have a GFRP reinforced member and you're putting an anchor in that member, should you take advantage of the FRP reinforcement the way you would take advantage of steel reinforcement that kind of reinforces the anchorage zone? I think that there's probably better ways of treating it than just treating it as plain concrete, but there is no specific language in 440.11 for how that would be treated. So it would be I think it would be a conservative approach to treat it as plain concrete. But I think that's maybe something that the 440 committee can think about for one of the next versions of the code is, how do we take advantage of FRP reinforcement for that scenario?
Yeah, you mentioned about few documents earlier, so there is another question regarding it, that does ACI 350 allow use of GFRP rebars for environmental structures such as fluid retention tanks?
Yep, another really good question. Short answer is no, there's no reference to GFRP reinforcement in ACI 350 currently. And there's a lot of design issues in 350, water tightness, crack spacing, crack width. I think that would possibly be quite a bit different with GFRP. So I think as we kind of mature in having codes available for GFRP reinforcement, that's one area that has been talked about. How do we include FRP in other ACI codes? We're not there yet, but not to say that FRP can't be used in those applications. It's just there is no code for using that in those applications. So there's a little bit more research maybe that's needed. There's a little bit more design effort that's needed, but those are not part of that code currently.
Okay, so our next question is, how feasible are GFRP bars for areas with less stable soil?
For areas with less stable soil, so I guess a couple things come to mind. If we're talking about things like expansive soils, I would say that FRP reinforcement can be designed according to requirements in 440.11, the way you would design a steel reinforced element under those conditions. So whatever type of foundation system you're using, you could design it to resist the expansive forces of the soil the same way you reinforce using steel. There are some things, though, that also come to mind that you do have to watch out for. If there are things like sulfate attack that are a potential problem with that particular environment, that particular soil, FRP isn't going to help you. Sulfate attack is going to attack the concrete. It's a concrete deterioration mechanism. FRP is not going to do anything to necessarily slow or stop that. So if the issue with the soil is more from that standpoint of the chemical attack on the concrete, then certainly FRP could be used, but it's not going to be beneficial. It's not going to prevent that from happening.
Okay, so we are turning to our last question. It's can we use GFRP bars in tunnel concrete ring?
In a concrete ring, is that the question?
I think it's more about tunnel concrete ring. So.
In a tunnel application?
Yeah. Mm-hmm.
It can. So the bars, we talked about the bars not being able to be field bent, and you can't bend a hook in a GFRP bar in the field, but you can bend them in larger diameters, 5 foot, 6 foot diameters. You can bend the bars in larger diameters like that. So the use of the bar in a ring type structure certainly can be done. You've got to be concerned with all the other things that you're concerned with using GFRP reinforcement, making sure the bars are spaced closely enough that you don't have crack widths that are too large in a tunnel application. If it's a vehicular tunnel, fire considerations might be an issue, but from a practical perspective, yes, you could certainly use it in a ring or any type of circular type structure, larger diameter circular type structure like that. Absolutely.
Great. Yeah, thank you so much, Will. This ends all the questions, and we really thank you for accepting our invite to answer these questions, and these will be really helpful for industry applications, and this will help the industry because GFRP reinforced concrete is new and it's hard for the industry to accept it, and it is different than how the steel reinforcement is used, and ACI 440.11 covers those differences, and it also gives you guidance how to use, and also the upcoming 2 manuals will help designers, contractors to design GFRP reinforced concrete structures. Thank you.
Yeah, thank you. Appreciate all the great questions that everybody had. Hopefully we can do more of these webinars down the road and answer even more questions. So my pleasure.